Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 2 of the video series on radicals, and we'll continue to perform operations on expressions containing them. So this is just a continuation from video 1. Let's look at question 2. This is on reducing radicals, and we use the perfect squares chart to reduce radicals. Okay, the key formula, aka identity, we need to discuss that first. And we've already seen this in our previous slides. The square root of a squared dot b is equal to a dot root b. So essentially what this means is that if you have a perfect square, if you have a product inside a radical, and one factor happens to be a perfect square, whereas the other factor is not, you can always extract the a from inside the radical to the outside of the radical. Why? Because the square root of a squared is just a. And that enables perfect squares to be extracted outside the radical. Do you recall that I called a squared SpongeBob? Because SpongeBob loves to be a perfect square because he gets to come outside the jail. Okay, the square root is just the jail. So the square root of a squared dot b is just a dot root b. Okay. Again, the restrictions on a and b have to be both greater than or equal to 0. Here's a little example before we start. The square root of 50, you ask yourself, what's the largest perfect square that goes into 50? And I can think of the largest one being 25. 25 is certainly a perfect square, and it's the largest perfect square that goes evenly into 50. So I can decompose 50 as square root 25.2. 25 is the perfect square. That's the good guy. And 2 is the bad guy because it's not a perfect square. You can rewrite 25 as 5 squared. The square root cancels out to 2, and then the 5 gets to come outside. So we get 5 root 2. So essentially that square root cancels out that 2, and the 5 gets to come outside. And the 2 remains in jail because it's not a perfect square. Okay, so using this concept up here, we're going to try to reduce some of these radicals down here. Let's look at part A. Over here we have 1/4 dot square root 54 minus 1/4 dot square root 150. The idea is to reduce the square root of 54 and reduce the square root of 150 if we can. Sometimes we can't reduce radicals because there is no perfect square that divides into the argument. And so therefore we're left with whatever we had to begin with. Okay, so not every radical can be reduced, but 54 can certainly be reduced because the largest perfect square that goes into 54 is 9. So we write 54 as 9.6. That's the decomposition. And the largest perfect square that divides evenly into 150 is 25. So we can write 150 as 25.6. And then the square root of 9 over here is 3. So 3 times 1 is 3. We can write 3/4 on the outside, and we're left with 6 inside the jail. Over here, the square root of 25 is 5. We can bring the 5 on the outside, and of course 5.1 is 5, and we get minus 5 over 4 root 6. So the 6 again is left inside the jail. Okay, then you can use a little bit of backward bin gathering over here. You don't really have to because it's so simple, but I do it anyway. Okay, the square root of 6 over here is common, so we can open up a root 6 bin and drop in a 3/4 and then drop in a minus 5/4. When you simplify this, You get 3 minus 5, which is negative 2. And then negative 2 over 4 is negative 1/2. And you can rewrite it as negative 1/2 dot square root 6, which in turn can be rewritten as minus root 6 over 2. You could leave it like this. I have no problem with that. Or you can leave it like that. It's completely up to you. A lot of things in math are optional. Some things are and some things aren't. Okay? But this is certainly optional. You can leave it as minus 1/2 dot root 6. Or you can rewrite it like this. Let's go on to the next slide. Let's look at part B here. We have 2 root 20 plus 3/4 root 80 minus square root 125. So again, the objective is to try to reduce each of these radicals if possible. 20 can be rewritten as 4.5, 4 being the perfect square and 5 being the bad guy. 80 can be rewritten as 16.5, 16 being the perfect square and 5 is the bad guy. 125 can be rewritten as 25.5. 25 is the perfect square and 5 is the bad guy. Okay, so now we can extract all the perfect squares. In the next line, when we extract the 4, the square root of 4 is 2 and 2.2 is 4, and we're left with a root 5. When we extract the 16, the square root of 16 is 4. 4.3 over 4, the 4's cancel, and we get a 3. So we get a 3 root 5. The square root of 25 is 5, and we get a minus 5 root 5. Now, they all involve root 5, so they're all bad guys. And then you can either use backward bin gathering, or you can use the little apple trick. We have 4 apples plus 3 apples minus 5 apples is 7 minus 5, which is 2 apples. So we get 2 root 5. Let's go on to part C. We have 1/2 square root 8 plus 3/5 square root 50 minus 2/3 square root 18. And again, the idea is to reduce these radicals if possible. 8 can be rewritten as 4.2. 50 can be rewritten as 25.2. 18 can be rewritten as 9.2. Again, 4, 25, and 9 are the perfect squares, and 2, 2, and 2 are the bad guys. Okay, now it's time to extract the perfect squares. The square root of 4 is 2, and 2.1/2 is just 1, so we don't have to write it down. And the square root of 25 is 5, and 5.3/5 is just 3. And the square root of 9 is 3, and 3 dot minus 2/3, the 3's cancel, and you get minus 2. So I notice what I'm left with is just a root 2, so I open up a root 2 bin. Over here I pick up a 1, over here I pick up a 3, over here I pick up negative 2. And then you just simplify inside the bin. We get 1 plus 3 is 4, minus 2 is 2. And finally we get 2 root 2 as the final answer. We'll just continue with part D. We have 2 over 5 dot square root 125 minus 2/3 dot root 243 minus 1/2 dot square root 48. And it's time to try to reduce the radicals. I notice that 125 can be rewritten as 25.5. 243 can be rewritten as 81.3. And 48 can be rewritten as 16.3. Okay, if you can't figure out these perfect squares over here, I suggest you go back to the perfect squares chart. Okay, we're always looking for the largest perfect square that divides into 125, the largest perfect square that divides into 243, and the largest perfect square that divides into 48. And those perfect squares are 25, 81, and 16. You can get those from the perfect squares chart. Let's continue. Now we're going to extract the perfect squares. We get the square root of 25 is 5, and 5.2/5, the 5's cancel, and you get a 2. The square root of 81 is 9. 9.2/3 is minus 6. We get minus 6 root 3. And over here, the square root of 16 is 4, and 4 dot negative 1/2 is negative 2. So we've got, at the end of the day, over here we have 2 root 5, and then minus 6 apples minus 2 apples is minus 8 apples, so we get minus 8 root 3. So at the end we get 2 root 5 minus 8 root 3, and we are done. Let's go on to the next slide. Question 3 involves rationalizing monomial denominators. Monomial means a single term, no plus or minus, not like binomial, not like trinomial, monomial, one term. Okay, and notice specifically the denominator. Let's look at the key formulas, aka identities, first, before we proceed to do any questions. 1 over the square root of a. Normally, in mathematics, we do not like to see radicals in the denominator. Okay, so if we remove any radicals in the denominator, it's called rationalizing. So when somebody says rationalize the denominator, it means to remove the radical in the denominator. So it's a very fancy word for annihilate the radical in the denominator. Okay? I could care less personally. If I have radicals in the denominator, so be it. Mathematically, it makes no difference whether you do or whether you don't rationalize. Okay? But what can I do? I'm only one person, and everybody else seems to want to rationalize the denominator. So here I am. I'm going to try to teach you how to do it. Okay? So apparently, we don't like to see the square root of a in the denominator. The idea is to multiply top and bottom by the square root of a. On top, we get 1 dot root a, which is just root a. And on the bottom, we get root a dot root a, which is, of course, a. Okay, so altogether, we can rewrite 1 over root a is identically equal to root a all over a. Now, in my books, this looks easier than this. Okay, so I prefer this to this, but your teacher may not prefer this to that. They may want this. What can I tell you? You know, you'll have to deal with your teacher in that regard. Restriction. A has to be greater than 0. It has to be greater than or equal to 0 because of the radical. It has to be strictly greater than 0 because otherwise we get division by 0. Okay, so be aware of that, the restriction on the argument. Here's a simple example. 1 over root 2 occurs very often in trigonometry, and you can either write it as 1 over root 2, or what you do is remove the radical, put the radical up top, and put a 2 on the bottom. So essentially, look at this again over here. All you're doing is what you're doing is grabbing that radical, putting it on top, and then erasing the square root and putting it on the bottom. Again, all you're doing is grabbing that radical, putting it on top, erasing the radical, and putting the argument on the bottom. Okay? So 1 over root 2 is identically equal to root 2 over 2. Just like 1 over root 3 is identically equal to root 3 over 3. Okay? So etc., etc. Here's another important formula that you can use. Essentially, this is just a more general version of this guy up here. Essentially, if you have a good guy, square root bad guy, and a good guy, square root bad guy, this is essentially what you do. And again, this is an identity. If you multiply top and bottom over here by the square root of d, on top you get a root b dot d, and on the bottom root d is just d, so you just get c dot d. So again, a root b all over c root d is identically equal to a root b dot d all over c dot d. So essentially, what do we do over here? Okay, think about this carefully. All you do is grab that d, put it beside the b, and remove the radical. Grab that d, put it beside the b, and remove the radical. That's exactly what it means. Okay? Grab that d, put it beside the b, inside the radical, and then remove the radical symbol. Okay? So it's effectively the same as this. Okay? Again, the restrictions. B has to be greater than or equal to 0 because it's in the numerator, and d has to be strictly greater than 0 because it's in the denominator, and you want to make sure you never get division by 0. Example, 2 root 3 over 3 root 2. Remember what I told you. Bring the 2 upstairs. You get a 3.2, which is 6. And then remove the radical, 3.2, which is 6 on the bottom. So altogether, you get 2 root 6 on top, and then 3.2, which is 6 on the bottom. It just so happens that 2 over 3, 2 goes into 2 once, 2 goes into 6 3 times. So this reduces to square root 6 divided by 3. Okay, so if you can remember this, this will come in really handy. Okay, so let's go on to the next slide. These are actual questions that we can do. We're rationalizing monomial denominators. Again, these are single term denominators. So again, doing what I just finished doing on the other sheet there, or the other slide, 1 over root 3 can always be rewritten as, all you do is grab this guy, put it in the numerator, and erase the radical. Okay, again, grab it, put it in the numerator, erase the radical. You can do the same thing over here. The 2 just goes along for the ride. What you do is grab it, put it in the numerator, erase the radical, put it in the denominator. Again, 2 goes along for the ride. Grab the radical, put it in the numerator, erase the radical, put that in the denominator. So that's a quick way of doing it. Alternatively, you can multiply top and bottom by the square root of 5. On top, you get 2 root 5, and then root 5 is just 5. So it's exactly the same thing. Okay, so it's up to you which way you do it. If you want to use my little identities, you can go ahead and use them, or you can multiply top and bottom by the radical that you wish to annihilate. Okay, so we have 2 over root 7. Can be rewritten as 2 root 7 all over 7 using the same ideas that I've used before. It's very, very quick. This is the same sort of thing. The 2 goes along for the ride. 1 over 2 root 3 can be rewritten as, all you do is pick up the root 3, put it on top, erase the radical, put it on the bottom. And we get 2.3, which is 6, and you get root 3 over 6. Same sort of idea. The idea is to get rid of the radical on the bottom. The 3 over here goes together with a 5, and you remove the radical over here. So you get 5.3, which is 15, and then 2.3, which is 6. Alternatively, you can multiply top and bottom by the square root of 3. On top, you wind up getting 5 root 15, and on the bottom, you get 2.3, which is 6. Completely up to you which way you want to do it. Let's go on to the next slide. And more of the same thing. We've got 2 root 2 over 2 root 18. This over here, you've got to be clever. Notice that 2 and 18 has a common factor of 2, so you can reduce. Even though they're inside the radicals, you can simply reduce. 2 goes into 2 once, 2 goes into 18 9 times. The square root of 1 is 1, so you get a 2 on top, and then the square root of 9 is 3. So we wind up getting 2/3 right off the bat. There's no need to multiply top and bottom by the square root of 18 when you get a reduction here, when the fractions reduce. Never mind the radicals reducing, when the fractions reduce. Here's another problem, the same sort of thing. We have 4 root 2 all over the square root of 8. You can multiply top and bottom by root 8, but that's overkill. You get 2 over 8 is 1/4. You get 4 root 1 on top, which is 4, and the square root of 4 is 2. So we wind up getting 4 over 2, which is 2. Over here, there is no reduction, so you have to do it the long way. You can multiply top and bottom by the square root of 3. On top, you get 3 root 15. On the bottom, root 3 is just 3. And then you can cancel out the 3's, and you get root 15. And root 15 is irreducible. Okay, again over here, I notice this time there's a cancellation. I can reduce 7 over 14 to 1 over 2. Okay, so, and I can also reduce 4 over 2 because 4 over 2 is just 2. I put the 2 down there. And then 7 over 14 is just 1 over 2. The square root of 1 is 1. I didn't even write it down. and on the bottom you get the square root of 2. And then you can multiply top and bottom by root 2 if you wish. And on top you get 2 root 2, and on the bottom root 2. Root 2 is just 2. At the end you can cancel out the 2's, and you wind up getting root 2 in the final analysis over here, okay? J over here you get, we have 3 root 6 all over 4 root 10. And I noticed that 6 over 10 reduces to 3 over 5. And that's what I did over here. I reduced it to 3 over 5. And then if you want, you can multiply top and bottom by the square root of 5 to remove the radical in the denominator. Okay, when we multiply top and bottom by root 5, on top we get 3 root 15. On the bottom we get 4.5, which is 20. And 3 and 20 will not reduce, and 15 cannot be reduced either, so declare that to be the final answer. And then K over here we have 7 root 11 over 2 root 3. 11 over 3 won't reduce, so you can't do anything there. 7 over 2 won't reduce, so you can't do anything there. So if we multiply top and bottom by the square root of 3, on the top we get 7 root 33, because 11.3 is 33. And on the bottom we get 2 dot root 3, which is just 3. So we get 2.3. So on top we get 7 root 33. On the bottom 2.3 is just 6. 7 over 6 will not reduce. And the square root of 33 will not reduce. So voila, we are done. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.